Good afternoon. Welcome to this particular lecture that is on the applications of remote sensing and geographical information system for disaster mitigation and management. So, before we proceed further, just small information on how do we, you know, classify hazard or disaster. As you all know, a hazard is a process, phenomena, or human activity that may cause loss of life, injury, or other health impacts like property damage, social and economic disruption, or environmental degradation. Whereas disaster, is a sudden calamitous event that seriously disrupts the functioning of community or society and causes human, material, and economic or environmental losses that exceed the community's or society's ability to cope using its own resources. So, hazard, if you see on the left, there's a picture that boulder is a hazard, and if it does not roll, it has the potential to cause damage, but till it is resting on the top and not causing a damage, it is a potential threat. That is what we mean to define as a hazard. And once that boulder rolls down and causes, damage to the infrastructure or the society or the habitation living downslope, that sudden event, sudden rolling of boulder will be called as a disaster. So that is the difference between a hazard and a disaster. And we often speak about risk. Risk is, an integral, or it is a multiplication of hazard that is defined here. Exposure, the people that are exposed on the path of disaster, and their vulnerability, that is means how their social and economic conditions, if we speak about the society, if we speak about the houses or the buildings, how old they are, what type of material they are constructed. So all that, if we put together, helps in assessing the risk. Now hazard has been classified in different groups, and this is a classification that is followed by emergency international emergency database, that is called EMDAT. It classifies hazards into geophysical, which includes earthquake, mass movement, volcanic activity; hydrological, flood, landslide, wave action; meteorological, storm, extreme temperatures, fog; climatological, drought, glacial lake outburst, wildfires; biological, extraterrestrial. So it classifies hazard into different six categories. Now we all know that disasters in recent times are exceeding. We are finding more intense nature of disasters. Their frequency of occurrence is also increasing, and the damage and the people which are affected or displaced is also on the rise. And there are statistics to prove that the average of last one decade, is now being equaled in one single year, whether it be in the terms of the events or the terms of mortality or people affected or the economic damages. There is also much clarity emerging that most of the disasters now are driven by climate change. And if you see last few years of disaster on the slide, you can see 2021 we have severe disasters like floods, hurricanes, all. And India also had two very severe cyclone, Taukte and Yas. All are driven by climate change, and they are causing lot of damage in terms of not only the mortality, but in terms of the monetary losses are also huge. Now during disaster, lot of information is required by the person who is leading, who is in the leading role. He has to decide at the time of the disaster, what kind of response action has to be planned. It requires lot of information where the disaster has occurred. you know what is the intensity of the disaster, what is the spatial dimension of the disaster, or there may be many other questions. What would happen in times to come, and how relief and rescue operations can be carried out. So at the time of occurrence of disaster, and not only in the time of occurrence, also once the disaster has happened, how the rescue or the no, relief and rehabilitation has to be carried out. And post disaster also, how the mitigation has to be done, or the early warning has to be done. So there are a lot of questions which require a lot of information for a better planning for in the entire disaster management cycle. And during disasters also, the timeline is very short and the information required is very high. In when technology was not so advanced, we used to have a ground based approach, or the conventional approach, where people used to go on the ground and do the survey or assess the area to answer all the questions that are needed to address whether it is response, mitigation, preparedness. But as the but in case of conventional means, the time is limited, the resources are limited, the area accessibility is lost, and manpower is also limited. You have lot of restrictions or constraints in various terms like finance, time. So with evolution of technology, especially the satellite based technology, this field of disaster management has been benefited to a great extent. Why so you can see in this slide that because these satellites are orbiting the earth, they are at a higher platform, they have a higher, they have a wider vision. They can see wide area is visible on the ground as compared to the human eye. And also because they orbit, they can again have a they can again come back to the same place and take the picture which is required to monitor any kind of dynamic movement, as in the case of floods, forest fires, or cyclones. And these the benefit of these satellite is that because they are at a higher altitude, we have coverage for the inaccessible areas. We can compare what was there before the disaster, or what has happened after the disaster. Temporal monitoring can be done, day 1, day 2, day 3, how the things are changing. And they are also able to operate in all weather conditions, whether the weather is cloudy or it is not so conducive at the ground. But because these satellites are at a higher altitude, they can observe the phenomena that is happening on the ground very comfortably. And they are also not prone to damages, unlike the instruments which are placed on the ground and can be damaged by various disasters, whether it is fire or floods or earthquake. And may stop recording the event because the instrument themselves get damaged. But since these satellites are orbiting at a higher altitude, they continue to observe the earth and provide information. So now, not only satellite remote sensing, but various other geospatial technologies also have evolved in time. Like the GIS, we have web GIS, we have mobile apps, we have a lot of other means of which are using various geospatial tools to report the phenomena from the ground. Like we have incident reporting systems, we have dashboards, we have simulation models, decision support tools. All are getting integrated and And today the emergency management framework has various kind of geospatial tools which integrate together to provide a better picture of the disaster, whether in terms of visualizing the event or simulating what could happen after a few days, or and next few hours, how the situation can evolve. And also the dissemination has improved through various dashboard services or the mobile apps. So these technologies have helped the disaster management to a large extent. ISRO has its own disaster management support program where they have various Earth observation satellites for the response, mitigation, preparedness, and early warning phase. These satellites help in preparing the input data or simulating the models or calibrating the models, and also preparing various layers like you require land use or the digital elevation models. Weather monitoring satellites are also available, from which like cyclogenesis or heavy rainfall phenomena can be observed, which can help in also help to for weather forecasting, or for or the models which require inputs for predicting the where the exactly the landfall will happen. Communication satellites are there which help to establish connection during the times of disaster when the terrestrial connection gets lost. Aerial survey facilities are also there. Early warning research work is being done. Geospatial support, all the inputs prepared during the disasters are disseminated through Bhuvan Geo portal and NDM. International support also is one field where the ISRO DMS program is actively contributing to various through various forums like International Charter, UN Spider, UNSCAP, Sentinel Asia. And next, capacity building is also one of the key important areas where the focus is to strengthen the capacity of all those people who are involved in the field of disaster, so that the space based inputs can be meaningfully used, prepared, and interpreted by the community who is involved in this particular field. And also support to various central and state agencies are provided proactively during the times of disasters, and as and when the agencies request for specific disasters also, the support is provided. Now before we move into further into some case studies, I just want to tell in general we have two kind of sensors: active sensor and the passive sensors. One is that which do not emit radiation themselves, and other are the which emit radiations. So one is depending upon the sunlight, and one is one which has its own source of energy. It can send a beam of or a pulse, and one which is depending upon the sunlight operates during daytime, like we have the multispectral sensors or the hyperspectral sensors. And whereas the those who have their own source of energy, like the microwave sensors, they are able to send their own pulses, so like radar sensor and lidar sensors. So they can operate during day and night because they have their own source of energy. This is the example of the active and the passive sensors. This one on the left is the optical image, and on the right is the microwave image. One is taken by the optical sensors and the microwave sensors. On the left, you can see because of the cloud during the monsoons, the land is not clearly visible, and all the the wavelength, whatever was radiation was passing has been blocked by the clouds, whereas on the right you can see a microwave image where these clouds do not make any impact, and due to longer wavelengths these clouds are penetrated, and the picture on the ground is clear, though both of the images are taken on the same date. One is on the 10th July, other is also on the 10th July, but one is acquired by the Indian remote sensing satellite which has an optical sensor, and the one is acquired by radar set which has a microwave sensors. So this is now, I'll just take you through some examples how these satellites help us. This is one example from MODIS satellite, which is called Moderate Resolution Imaging Spectroradiometer MODIS. It has Terra and Aqua sensors, which have passes in the morning 10:30, and Aqua has in the afternoon at 1:30, and they have a very wide swath, roughly more than 2,000 kilometers. So when you require to visualize a larger area, like in this case, we can see floods of 2010 in the Indus Basin. So pre on the top is the pre-image before the floods, and one is after the floods. So large, because of its large swath, we can visualize how the flood has evolved or happened on a larger area. Now this is other example where how the satellites can help in temporal monitoring. Now if we have continuous observations, like in this case, this example of cyclone Philene, when this cyclone Philene was approaching the coast of Odisha. You can see we had one observation from reset on 13th October 2030 at 6 hours morning. Then again on the same day we had 6 p.m., and next day again morning 6 we had observation from radar set. So continuously you had we had observation from morning till next morning, and you can see how the picture has changed. On the left, if you see on the yellow circle, there is no water, but in by the evening the rivers have started flowing in full speed, and a lot of there is a lot of inundation in the channel. And you can see the blue circle on the right, where there is no water in the evening image, but next morning you see a lot of fresh inundation has happened. So such kind of dynamic monitoring of the floods can be done through if you have continuous observation of data on the ground. And this is also required for continuously monitoring the flood progression, recession, and the persistence, how the flood is the water is persisting in some areas, or moving or receding, so that accordingly the steps can be taken to have mitigation measures on the ground. Like if we have areas where the water is getting accumulated for a larger number of days, so there may be chances of epidemic, or the crop wilting may start, or the water quality may deteriorate. So we need to have certain actions on those areas where the water is persisting for a longer duration. So these maps can help in that particular area. Once the disaster is happening, they can help us to map and monitor the event, like this example for Kosi floods in 2018, which happened for almost more than 1 month. It happens almost for 2 months. It happened in somewhere in August until I think in October also. This event was continuously happening because of the breach in the embankment. And that time the satellite pictures help to for the situation monitoring, relief management, impact assessment, and decision making. And these maps were being provided to the state relief commissioners as well as central agencies for relief rescue operations, for and these were also being used for prioritizing the villages where the flooding was more, or dropping of food packets in those particular villages. These satellites also have a great role, when the disaster happens on higher inaccessible areas, especially in the Himalayan terrain, where there is no accessibility of, where human beings cannot go so easily, not because of the lower temperatures, because of the rough undulating terrain. It is very difficult for an individual or the even the your helicopters or other cannot land in these areas. So satellite images are the only source which can provide information. And in this case, there is one Fukta Lake example in Jammu and Kashmir. This happened in 2015. There was a landslide, and due to landslide, lot of water accumulation happened upstream. And that time, NDMA wanted to have information about the dimension of the landslide, about the volume of the sediments deposited in the channel, and so that they can remove those sediments through their whatever ground measures they can take. So defense team and NDMA team together, they did some controlled blasting so that the sediments can be removed and the channel can the water is allowed to move freely. So these satellites helped to a large extent in knowing exactly what was happening there, how long was the impoundment, whether the water has frozen up, or how much material has got deposited. So these satellites have a great role in such areas. And when it comes to like damage assessment, if we want to have high if we want to assess damage, what has happened, like in the case of embankment breach, or how many villages have got submerged, or which roads have got submerged, or where how many settlements have got inundated by water, or the crop area has got affected. So depending upon our requirement, whether we want to have very high detailed damage assessment, we need to have very high resolution satellite data available with us, or if we want to have at a regional level, we can go for a coarser or a moderate resolution of data. In this case, you can see on the right bottom side, this is the data from Pledis at 65 centimeter, where each individual house roof can be seen. And on the left, you have data from Cartosat at 80 centimeter, where you can count the trees and the individual houses, and also the data from Sentinel 2 at 10 meter, and Terras RX maybe 10 meter. This data is also is able to show you the breach in the embankment. Now, once we have information from satellite about the extent of disaster, be it due to floods, cyclones, forest fires. Once we have that extent, the extent of the the hazard, that can be integrated with the land use, the villages, the roads, and the crop area to do the damage assessment, to find out how many, what is the length of the roads submerged, or how many villages are impacted, or how much cropped area has been affected by that particular event. In this case, it is the example, it is the floods. Now there are I'll just speak about one tool that is called satellite altimetry. This is a virtual gauge stations. In times of flood, we require gauge stations to measure the water level. What is the level of water at each site, or what is the discharge, so that we can calibrate our models, or we can do the analysis. But in times of floods, these gauge sites are lost because of the huge volume of water or the high speed of the water. These gauge stations also may get damaged. So satellite altimetry is useful in studying river discharge and reservoir volume, which can be used for calibration and validation of this hydrological and hydrodynamic models for generating rating curves, stage discharge relationship. So this technique, it emits radar pulses and receives the echoes reflected from the water surface. You can see on the center The red is the radar pulse, and green is the reflected echo, which can be collected once it strikes the surface of water. It goes back and is received by the sensor, and with an accuracy of few centimeter. This is, and we can derive the water level from the duration between the sending the pulse to receiving the echo. By the difference, before the floods the water will have some kind of level, and after the floods, there, because of the rise in the water level, there will be different time difference between sending the pulse to receiving the echo. And this difference is what helps us in finding, assessing the change water level. So India is also has is stake in this satellite altimetry. We have a mission with uh, French space agency Saral Altica satellite with Argos and Altica in 2013. This was the first high frequency Ka band 35.75 gigahertz mission. you know so this is also, this altimetry helps to have it is a kind of virtual gas station, where we do not, we can also supplement our ground observations with the satellite based observations for doing river discharge and volume variation kind of studies. This is one example where satellite images helps to monitor the river course changes and bank erosion studies. Because of the high sediment of water, these river courses tend to change, and rivers are dynamic. After some years, their course may change, and also lot of erosion. Due to erosion also, these courses may change, and they need to be monitored. How much changes are happening in the river course, or how much sedimentation is happening, so that accordingly the steps or preventive measures can be taken, and that is where these satellites help such kind of mitigation and management plans. Hazard risk assessment, we may have some, if you want to, in this case the example shows hazard is the flood. The extent of flood can be taken from the satellite images or by modeling. The flood depth also can be computed by using the modeling techniques. And exposure in this case, because of the flood, the crop, in this case it is a paddy crop, can get affected, and paddy crop can also be mapped using satellite images. And the next is the vulnerability. To find out risk, we need to have hazard, exposure, and vulnerability. And as you can see on the right, there is a graph which shows a vulnerability as a measure of, maturity stage and flood depth. If we have flood depth and the stage of the crop, and how many and the duration, we can find out what will be the yield loss, what of the crop. And there are standard tables which shows if the days of submergence, if the crop is submerged for 1 or 2 days, 3 to 4 days, 5 to 6 days, or 1 week, and the crop is at which particular stage, whether it is ripening stage, vegetative stage, maturity stage. If we have this information from ground, if we have how many days the crop is underwater, and if we have the plant height, because at different stages the crop will have different height, and we have the flood depth and exposure, so we can compute the what would be the estimated yield loss in this case. So risk assessment can be done. Similarly, for mapping and monitoring of snow covers is also important, because this snow excessive or high snow fall in higher Himalayan area has to be monitored, because it is important, which can increase the probability of flash floods, landslides, sudden increase in river flow, and associated hazards in the region. So heavy snowfall needs to be monitored, because that will increase the snow covered area, and that is important for various, hydrological forecasting or other kind of disasters, or other water resource related management actions. So this is the recent example you must have heard of Lunak Lake. That is a GLOF event happened in the state of Sikkim, in the higher Sikkim, where there was a lake, and due to the GLOF event, there was a high volume of water which outflowed from the lake due to various due to certain reasons, because of certain slope failures on the northern margin of the lake, the lateral moraine, of cutting and some carving of ice, and also there may be some possible avalanches which led to the breach in the lake, and the lake from its actual size or before the event got drained out. And you can see on the post image, this is a zone where the water got reduced, and there is now no more water. And this area, there was some kind of slope failure. There can be seen increase in the size of the lake and some changes in this particular slope. So the lake area change, we can see the change in the lake area. Also the course of the river changed before and after the event. There is change in the flow of the outflow of the water. And and also you can see how the changes in time. Here you can see deep clear water is there before the event, and then some due to fall in the temperature, some freezing also happened, and you can see the lake to be frozen at some places. So such kind of observations can be seen. And you can well remember that this was the first satellite from ISRO that brought out that in actual there is a certain kind of outflow that has happened from the South Lunak Lake, and the water has actually reduced in the lake, and due to which there was a lot of downstream destruction happened on the downstream site. And this particular picture shows there was an increase in the snow cover area between these two dates. And here you can see, because of outflow of the water, a lot of sediments have come down. And you can see this is the post pre-event, and this is the post event picture of 5th November, and this is the 14th May picture. But lot of sediments have settled in the floodplain of the river because of that particular event. This is downstream Chungthang Dam before the event, and after the event this dam was completely damaged. And due to this particular event, all the water has outflown. And this can be clearly observed from the satellite images. So satellite images also help you in the GLOF studies, GLOF modeling studies or the damage assessment. So all the studies can be helpful for flood forecasting and other kind of forecasting studies. Also these satellite images provide a lot of important input in terms of land cover, rainfall, elevation data, soil map, and setting up the model. All can be integrated or ingested into the model, which are again GIS enabled, and can help to in the rainfall runoff modeling, hydrodynamic flow routing, calibration, validation of the model with field discharge data. So all these activities can be taken up. This particular slide shows you how the satellite images not only provide you direct input from the observations. Like on the picture on the right side, we can see the flood extent. So this is a direct observation. But apart from direct observation, if we are into flood modeling or any kind of hydrological modeling we are doing, can simulate our model using the discharge data on the day when this event has happened. And by the modeling, whatever results come, we can validate with the satellite images, because this output has to be the flood modeling output also, more output has to be validated with some kind of data. So satellite images can be used to validate the output of this modeling. So the model calibration, validation, and data assimilation technique also, this remote sensing data helps, this is one of the studies that we have done for simulation of the flooding on in the Sabri reach by using HECRAS model, by giving the discharge data or taking land cover and river cross sections, how much extent will be flooded under different kind of discharges. For landslide inventory also, these satellite images help in creating the database. This is the example of the Kedarnath area where we have flash floods in 2013. So this yellow shows all the areas where the landslides have got activated or fresh landslides have happened. So these can be mapped and they can be an important input for our landslide hazard zonation mapping. So because landslide hazard zonation mapping requires different kind of input layers, and previous areas where landslides have happened can also provide an important input. Either they can also be used as a validation purpose, or also feeding into the model so that our accuracy of landslide hazard zonation mapping increases. These satellites help you in monitoring the cyclonic hazards, their cyclogenesis, or the predicting the cyclone track intensity and the rainfall. For mapping of the oil spill in the that happens in the sea area, either due to movement of ships or due to collision of ships. This is an example of 2017 where in Chennai area, close to Chennai area, two ships collided near the Kamraj port, and due to which a lot of oil spill happened. And because this is the data on the left pre-event and right post-event. These are microwave images, and in which all dark area can be clearly seen as the oil spill because of their specular reflection, and all bright areas are the ships moving in the sea. So we can monitor the spread of the oil spill. For drought monitoring also, satellite images are being used to a large extent, where the vegetation status, how the vigor of the crop is there, can be monitored by using different indices. And also the taking various other inputs, or like rainfall or other meteorological parameters. So drought monitoring can be done. These healthy crops and the crop that are under stress have a different kind of reflectance patterns in in different wavelengths. You can see on this particular graph, the normal crop, this healthy vegetation is the green line, and whereas stressed vegetation is the orange line. So at NIR, there is a high reflectance, whereas as compared to the stressed vegetation, whereas in the red band, in the green band also they behave contrary. So this this and also in the middle infrared. So this information can be extracted from the satellite images, then NDWI, EVI, soil moisture, rainfall, soil information, rainfall information, all can be integrated to have various drought monitoring studies. uh, in case of land deformation, also satellite images play a large extent, and these days are becoming very important, especially in case of land deformation, where no other technique can be so useful. This SAR interferometry, by looking at SAR images of the same area that have been acquired before and after an earthquake. Two sets of data can be compared. That is the phase. There is a change in the phase for each radar wave, and interferogram can be generated. You can see on this particular on the top, There is the first acquisition when the building is normal, signal is transmitted and signal is received. So this is phi, and there is after some time due to land deformation or some kind of movement, subsurface movement, this particular building has changes position in z dimension. So there is a phase shift, again when this signal is transmitted, this phi will have a change, and the change in the first pass, in the second pass, is what used to generate an interferogram. And interferograms created by using two SAR images that are acquired in two different times and maps the phase shift caused by a movement of the surface between two acquisition. Here also this example shows same thing, one first pass when the ground is normal, and then when there is a movement in the ground in the second pass. So this is what we used in, and most of the people around the world are using for Joshimat, land deformation analysis, where different kind of techniques, PSNSAR, SBAS, are being used to study the land deformation. And we also have used SAR interferometry to find out the areas where the movement, the rate of movement or line of sight, displacement is high. And in this case for Joshimat, this movement was varying between -26 to -12 during we the analysis was done from May 2019 to April 2023. And all this, you can see this has a high movement, downslope movement. This further has been, this at different points it has been compared, and we can see somewhere around 2022 this there was a increase in the movement, and in the early 2023 again this movement was more conspicuous as compared to in 1920 or 2021. This we have compared with the continuous operating reference station CORDS data, and also with the line of sight displacement, and similar observations are meeting with the INSAR observations. This is one example of forest fires. In case of forest fires, the temperatures are very high on the ground, and it is very difficult for a person to visit the area. Then also these satellite images can help you to provide the areas where the forest fires are active, or where the smoke is more in the valley, so that appropriate actions can be taken. This is examples of 2018 Uttarakhand forest fires, where you can see the active, you can see dark, red, red or orange flames, which are showing the this is the part where forest fires are active, and dark, these are burnt scars where the forest fires have already damaged the forest cover. So we can use for burnt area mapping and monitoring. There are satellites, you must have heard during the COVID period, a lot of Sentinel 5P, images were being used around the world to show that there is a drastic change in the pollution levels, especially in and around the areas like metros, or which were heavily industrialized areas. There is significant change in the level of certain gases. So this TROPME, the Sentinel 5P from ESA, has a instrument called TROPME, tropospheric monitoring instrument, and this onboard Sentinel 5P means precursor satellite, and it helps to map a multitude of trace gases such as nitrogen dioxide, ozone, formaldehyde, and many other gases. And we can see how there was drop in the concentration of these gases in around these places. Satellites can also help you to monitor volcanoes, because during volcano there is lot of thermal, there is an increase in the temperature. So changes in the temperature also can be monitored, and these thermal anomalies can be monitored, and so it helps to monitor the places where volcanic eruptions are there, using different kind of data sets. This example I want to just bring to your notice, that people have used satellite images to predict infectious diseases outbreaks. For infectious disease, you have used NDVI, which indicates the greenness of vegetation, and NDVI anomalies reveal how much healthier greener vegetation is it is there. And greener areas are usually water wetter. If the crop is healthy, that means it has good amount of water there, it is not stressed, suggesting better habitat for mosquitoes. So those areas are the areas where mosquitoes will have better habitat, better suitability for breeding. So favorable conditions for mosquitoes, this example of red of the Rift Valley outbreak in Eastern Africa. So they have done a study where there was more cases of fever, Rift Valley fever. So they have detected that there was good amount of greenness in the areas, uh, and those areas have had a higher spread of this particular fever. And also for the locust attack, these images have been used for monitoring soil moisture and vegetation from space using satellites. And it shows the maps on the space show two important environmental parameters for locust development: soil moisture and vegetation. Soil moisture is important because females almost always lay their eggs in wet, warm, sandy soil. For laying of eggs, they require wet, warm, sandy soils. In general, they do not lay their eggs unless the soil is moist down to 5 to 10 centimeters. So this is the kind of already available observation that 5 to 10 centimeters of soil moisture is there. After eggs hatch, the abundance of nearby vegetation becomes the important parameter because it provides sustenance for maturing locust and guides migration patterns. So you require soil moisture, you require good vegetation, and that can be used to predict the movement of the locust, or the breeding of the locust, and how their movement will be there. Once the eggs are laid, they migrate to areas which have good vegetation. So this these people have used such kind of data sets to for the locust attack. So this is example that I have, few of the example that I have tried to bring out how these satellite images can help in case of floods, cyclones, locust attack, in case of spread of infectious disease, gloves, mapping of snow cover area, land deformation studies, forest fires, all there. And there are there are many more applications which can be taken up from the satellite images, not limited to what I have spoken here, but these are broad. But apart from this, like for tsunami also, it plays an important to monitor the hazard, and also for other kind of disasters, like health hazards also, or for the atmospheric pollutions, or any kind of industrial hazards also. Satellite and geospatial technology can play a role to a great extent. So I hope I have been able to give you some kind of flavor of how these satellites can help in assessing the disaster. Thank you for patient hearing.